In this tutorial, we're going to talking about the curve fitting method. So in this curve fitting method, we already talked about how in curve design we seek to talk about two things. The first of which is curve representation, second of which is shape control. So now when we're talking about the oldest method of curve design, we talked about two methods. So the first method was the curve interpolation method, which we already discussed in the previous tutorial. So we talked about the Newton divided difference approach. We also talked about the Lagrangian interpolation method. So now the second method of curve design, which is curve fitting method. So in curve fitting method, what we're trying to do that we're just trying to also get a polynomial equation that represents the curve. So now let's take a look at this what we have on this board. So we said that consider a set of n data points, which is x1 and y1. So now because every point is like a coordinate, so we have x coordinate and we also have the y coordinate. Since we're considering just a Cartesian plane just in two dimensions. So now if we consider the set of data points xi comma yi, so of course I is ranging from 0 to n minus 1. That's why we always start from x naught and then we always end the next 3 even though we have 4 data points. So now which have been best fitted by a quadratic polynomial. So this is the quadratic polynomial for this curve fitting method, that is y, which is equal to p of x. But now our equation for this curve fitting method is that a naught plus a1 of a1 multiplied by x plus a2 x squared. So now this particular curve now, this is the equation that has been best fitted to represent those data points. So just understand that part. So that is this equation is the equation that was best fitted to be able to like represent these data points that were given. So now the coefficients here now are still unknown. Remember that we don't know what a naught is, we don't know what a1 is, we don't know what a2 is. So now the main aim of applying this method is that if you can get these coefficients, if you can get what our a naught is, if you can get what our a1 is, if you can get what our a2 is, then slotting those values back into this equation, you can get what our a naught, a1 and a2 are, then we can see that we've already gotten the polynomial equation, or the equation that best represents the curve. So now going further with what we have on this board now, we say that these coefficients a naught, a1, a2 are unknown presently at these points where x is equal to xi. Remember that I itself is varying from 0 to n minus 1, right? So we want to get the coefficient of this particular equation a naught, a1, a2 at those points, that is points where x is equal to x naught. So now when x is equal to x naught, when x rather is equal to xi, so which means that our anywhere we have x, we're going to substitute that with x subscript I. So which means that yi is also going to be equal to p, which is a function of xi. It's also going to be equal to a naught plus a1 xi plus a2 xi to the second power. So which means that if you can get at these points now, if you can get what our a naught, a1 and a2, if you can get these values, putting them back into this equation, then we can see where they arrive at the equation that represents this curve, right? So we say that, and therefore the error in the ordinate value. So what we mean by ordinate is just y. Y coordinate is your ordinate coordinate, and your x is your abscissa. So the error in the ordinate value, that is in our y value now, that is sigma I, is going to be equals to yi minus. So what we just did is that we already know what our yi is, right? We also know what our whatever this term is, a naught plus a1 xi plus a2 xi squared. So if you have to subtract the value of yi from whatever you have here, if there's any difference, if there's any discrepancy between that, then that is your error value. So now we're saying that the error value, the error in the ordinate value now is going to be given as sigma I, which is going to be equal to yi minus whatever you have here. So you remember that I was saying that that discrepancy, that error value, if they are not coherent with each other, there's going to be the error. So now, once we already know this error now, if we are to square this the value of this error, then add the value of this error at different points, that is for I. Because we know we said that I now is varying from 0 to n minus 1. So now, if you have to square this error value, so square this value now, then add the error value for when I is equal to 0 to when I is equal to 1, when I is equal to 2, when I is equal to 3 to infinity. That means depending on the amount of points that are given in the question. So if you are given 5 points, you're going to stop in where I is equal to 4. If you are given 3 points, you're going to stop in where I is equal to 2. If you are given 4 points, you're going to stop in when I is equal to 3. Remember that you're starting from when I is equal to 0, right? So as I've already said now, when we square this value now, the value of the error, that is the error value of the ordinate. When we square that value and add the error value for each of those data points that were given in the question, then we can say that this is going to be the resultant error value that we're going to get, right? So now, to now get what we're looking for, remember that the main aim of following this process, right, in the first place, is to get what our a naught is, get what our a1 and what our a2 is. So now, after following all this process now, to now get this our unknown values now, what we can do is that our a naught, our a1, our a2, it can be determined by minimizing this error value. You know that this is the resultant error value by squaring and adding the error value at each of those data points are given. That is 0, 1, 2, 3. You are given 4 data points. So now, if you now want to get our a naught, a1, and a2, so you can do that by minimizing this value. When you minimize this error value, and then how do you minimize it? Minimize it by differentiating the error value with respect to AR, right? So when you do that and you differentiate this expression, right, with respect to AR, and of course R also is varying from 0 to 1 and to 2. So when you do that and you differentiate this value with respect to AR, then at that point you'll be able to find your A1, your A 0 and your A2. It might seem more vague now, but you're still going to understand very soon, right? So when you do that, so we're going to be doing that now. So we're going to be considering the question that we solved in the previous question. That's in the previous application of the Newton divided differential method, and also for the Lagrangian interpolation method. So we're going to apply that and see. So the caveat with this method now is that this method is a curve fitting method. So we're trying to find the best fit. So it might not give you the exact answer, but it's going to give you the closest answer to the original answer. So you can only see clearly say that which have been best fitted by a quadratic polynomial, which means that it's just the best fit. It is not the actual fit, but it's the best fit. So it will give, and because it's not the best fit, that's why we even have the error value in the first place. So if it was the perfect fit, then there will not be any discrepancy, there will not be any error. But because we are trying to fit the curve, we are trying to get a quadratic equation. We're going to get this quadratic equation, right, that can represent the curve. So once we get the quadratic equation, we try to plot it on the graph in the xy coordinates, and we get that particular curve. The curve is just the best fit based on the equation or the quadratic equation that we already gotten by solving giving using the given data points. All right, so going on, so let us now consider the question. Or before we even go solving the question now, let us try to minimize this error and see how we can get our a naught, our a1, and our a2. So what we want to do now is that we want to differentiate this error value with respect to a subscript r, and r varies from 0 to 1 and to 2. So now doing that, we're going to differentiate this entire term. All right, so this is what we arrived at from what we have been talking about so far, right? So we already have this error value now, and we said that we can get our coefficient, our a naught, our a1, and our a2 by minimizing this. And how do we minimize this? We minimize this by differentiating this entire expression with respect to AR, and AR varies from 0 to 1 and to 2, right? So, and that is because of the data point that we're given. We're given 4 data points, and that is why we have that, right? So now, going on now, to differentiate with respect to AR, we're going to have that this error value, which is delta. So the delta d AR. So this is a partial differentiation. So it's going to be equal to, so by the time you do this now, you're going to have 2, so 2, then summation of I to 0 to n minus 1. You're still going to have your yi minus, then you're going to have a naught plus a1 xi plus a2 xi squared. So this is going to be 2 minus 1, so this mean minus, this mean 1. So now remember that we are applying this method for differentiation. So we also have substitution method. So we also have to multiply it by the derivative of whatever is inside this bracket. So by the time you differentiate the partial with respect to AR, what you are going to get is this. So it's going to be multiplied by, that's going to be minus into bracket 1 plus xi plus xi squared. So this is what you're going to have as the resultant by the time you differentiate this, right? So now, if you go further to simplify this, you're going to get that our d, because it's a partial differentiation, so our delta source is going to be partial. So partial, this delta over the AR going to be equal to, this minus can come up here, so we're going to have minus 2. So now this entire term now, instead of writing this entire term always, we cannot represent it as xr. So we cannot write it as xi to the power of r. So this, that what this entire term represents. So this is the a kind of way of noting it. So we are just trying to compress this expression into x subscript I raised to the power of r. So if I've already compressed this, our minus has already gone to the 2. But let's this expression. So that is the summation. So that is the summation from I equals to 0 to n minus 1. Then we're still going to be left with our yi minus our a naught plus a1 xi plus a2 xi all squared. then we're going to have on minimizing this error value, right, by squaring the expression and adding it for all data points that we're given. This is what we arrived at. So we said that we minimize this by differentiating with respect to this AR, right? So then remember that at any turning point, it's always equals to zero. So derivative is always equals to zero. So when you differentiate the function with respect to the independent variable, it's going to be equals to zero because at the turning point, our derivative, our slope is always equals to zero. So slope is equals to zero. So which means that we can equate this value that we have here as zero because we have the understanding that slope is equal to zero because slopes are like turning points, right? So we know that whatever we have here, this expression is equal to zero. So we just know that for a fact. So all this is equal to zero. So now remember we also said something that r varies from 0 to 1 and to 2. So if our r, remember that we're multiplying this by this, so this is not a, it's not a subtraction. Let's take note of that. It's not a subtraction, it's a multiplication. So there's a product here. I'm multiplying this by this. So by the time this and this goes there. So this entire expression is represented by this xi raised to power of r. So now r is ranging from 0, 1, and 2. So now when r now is equal to, when r is equal to 0, when our r is equal to 0, what are we going to have now? So let us now further simplify this. Applying anywhere you see r, just put 0 there. So it means that xi raised to power of 0 is 1. So we can say we can just omit the xi, this entire expression that we represented with this xi. So now we're going to be left with just n raised to power 0 is 1. So we're going to be left with minus 2. Then we're going to have the summation of I to 0, n minus 1. Then we're going to have yi minus a naught plus a1 xi plus I'm going to have a2 xi squared. Then all equals to 0. They were not done yet. So what we can do is that we can further expand this. So if you are to open this up, you're going to have minus 2, right? So in fact, this minus 2 can go because if we divide both sides by minus 2, then this minus 2 take away this 1. So I'm going to be left with this exact expression. So opening this up, we're going to have the summation of I equals to 0 to n minus 1 yi, then minus the entire of this. We're going to have the summation of I equals to 0 to n minus 1, then a naught plus a1 xi plus a2 xi all squared. So all this is equal to 0. So we can take either one of these terms to the other side. So if I take this to the other side, it means that this negative becomes positive. If you take this one to the other side, then see multiplying throughout by minus 1, we're also going to have the same answer. So it means that our summation of I equals to 0, n minus 1, y of I is going to be equal to summation of I equals to 0, n minus 1, yeah. So into bracket a naught plus a1 xi plus a2 xi all squared. So this is what we're going to have now. So we can call this our equation 1. So this is going to be our equation 1, or we can just leave it the way it is. So what we have beneath here, that's our first equation that we're able to arrive at. That is when our r is equal to 0, is that summation from I equals to 0, n minus 1. That is off. So let me now open it up now for a naught plus summation of I equals to 0, n minus 1 for a1 xi, then plus summation I equals to 0 to n minus 1. Then we have a2 xi all squared. And all this is equals to the summation of I equals to 0 to n minus 1 of yi. So this is our first expression we're able to arrive at. So on the first condition, the second condition rather will now be when r is equals to 1. So now we can actually go through everything from the first step and try to put r as 1 here and try to expand everything. But what we're going to find is that if r is going to be 1 here, which means that xi raised to the power of 1, or just simply xi, is going to multiply the entire bracket, which means that this xi now, since it's now carrying I, is going to be yi multiplied by xi. Then inside the bracket also, we're going to have xi multiplying each and every of the terms. That's provided that r is equals to 1. So now, so that we don't have to go through the entire step again, we already know that simply xi, when r is 1, is going to multiply each of these terms. So you cannot say that when r is equals to 1, what we're going to have instead will now be summation of I equals to 0, m minus 1. Xi is going to multiply this because we're going to open the bracket here. So we're going to be having a naught xi, then plus summation of I equals to 0 to m minus 1. We are going to be having a1 xi dot squared because xi and xi is going to give us xi dot squared. Then plus summation of I equals to 0 to m minus 1. That will be a2 xi raised to the power of 3. Then all is going to be equal to the summation of I equals to 0 to m minus 1. That's going to be xi yi because xi is also going to multiply that particular yi. So now for the next condition is now when r is also equals to 2. Remember we said that we minimize this error value by differentiating the error value with respect to ar, right? Provided that r is ranging from 0 to 1 and to 2. So now the third condition is that when r is equals to 2. So if you have to replace r here with 2 now, which means that we're going to multiply each and every of these terms by xi squared. So not to go through everything again, I'm just going to say that our expression that we're going to arrive at is going to be summation from I equals to 0 to m minus 1. So for his first one now, we're multiplying by xi squared now because r is equals to 2. So that's going to be a naught xi squared, then plus the summation of I is equals to 0 to n minus 1, then a1 multiply now by xi cube, then plus summation of I is equals to 0 to n minus 1, then multiply by a2, then xi raised to the power 4, then it's going to be equal to summation of I equals to 0, n minus 1, there's going to be xi squared yi. So now we already arrived at these three expressions for the data points that we're given. So what we can now do is that remember that the goal now is to find what our a naught is, what our a1 is, and what our a2 is. And we know that once we get this coefficient, once we get our a naught, our a1, and our a2, and then we slot them back into the original quadratic equation, and we can get our equation for our curve easily. So now what we're going to do next is that to solve this now, we are going to solve it in the form of matrix form. So now let me just write the matrix representation out. So alright, so to now represent it with a matrix now, this is the first condition when x, let me put it here, when r rather, this when our r is 0, this when our r is 1, this when our r is 2, right? So now to now write this form of a matrix because that is the best method of solving this. So to write this form of a matrix, we're going to have this. So each of these terms now, we're going to bring them out. So we're going to be having this summation of I equals to 0, m minus 1 multiplied by 1. That is for this first term. Then the next term, we're going to be having summation of I equals to 0 to m minus 1 multiplied by what? Going to multiply by. Remember that what we are trying to get now are these coefficients a naught, a1, and a2, not xi, right? So which means that when you are trying to write this form of a matrix, what is going to be the independent value or the value that we're trying to get is going to be this coefficient a naught, a1, and a2, not x, right? So because you can also decide to just expand this x as x naught, x1, x2, but we're not going to be doing that. So writing this out now, we're going to be having m minus 1, right? So what are left there is xi. Then the next thing is going to be plus. Sorry, there's not going to be plus here rather. So there's going to be summation of I equals to 0 to m minus 1. Then we're going to be left with xi squared. Then we'll go to the next term. Now remember, we're trying to use a matrix to represent this so we can solve it better. So we're going to have summation of I equals to 0, m minus 1. Then we're going to be having xi here. Then summation of I equals to 0 to m minus 1, xi squared. Then summation of I equals to 0 to m minus 1, xi cubed. Then this last term also, summation of I equals to 0 to m minus 1, then xi squared. Summation of I equals to 0 to m minus 1, xi raised to the power 3. And then summation of I equals to 0 to m minus 1 to xi raised to the power 4. So now this is for just the first part. So now we're trying to get our a naught, a1, and a2. So in this next, I'm going to have a naught, a1, and a2. Then all this is going to be equal to this other part now. So that is going to be summation of I equals to 0 to n minus 1. Then for the first one, we have yi. The next one is summation of I equals to 0 to n minus 1. We have xi, yi. Then we have the last one, summation of I equals to 0 to n minus 1. Then we have xi squared, and we have yi. So now this is what we now have. So which means that, so now if you are given a question now, you don't have to go through the entire process and start solving from the beginning. Once you already know that this is what you are going to arrive at, then you just go ahead and put your values inside to get it. So now we already gotten this matrix now. So to now solve this matrix now, so from the question you would have known what your all your coordinates for this now is a summation of xi, which means that to get the actual value that will be in this slot, it's going to be the summation of x naught plus x1 plus x2. Remember that here is n minus 1. So depending on the data points that are given, if you are given 4 points, it means that your n is going to be equal to 4 here. Because remember that we said from the Lagrangian interpolation method that n represents the number of data points that were given in the question. So if we know our n, if we know the number of data points given, let's say that our n is equal to 4, that is, let's say we're given 4 data points, it means that our n minus 1 is going to be equal to 3. So to not get the actual value that will be here now, it's going to be, since n is, so since this summation is ranging from 0 to 3, we're going to be having x naught plus x1 plus x2 plus x3 to get the actual value that will be in this slot. So now for this point also now, to get here now, we're going to be doing x naught square plus x1 square plus x2 square plus x3 square to get the actual value that will be in this point. So I'm going to do the same thing for each and every term that you have in this matrix. So once you get those values now, then then you would have known the value for this slot, this slot, this slot. In fact, all these slots here, you have also known the value for here, this also slot here. So the only unknown values now, which is what I've been trying to get from the beginning of this coefficient method, which is your a naught, your a1, and a2. That's going to be the only unknown value in this entire matrix expression. So now, the methods that you can now apply to solve this matrix, you can apply either the matrix inverse method, you can apply the Gauss-Seidel method or Gaussian elimination method, then you can also apply the Cramer's rule. So I think the easiest one to use to apply, because of you might be trying to raise against time when you're solving this question in the exam, right? So you're trying to raise against and being accurate to your answer and also to solve it as fast as possible. So Cramer's rule method is, so depending on you actually, sir, but if you feel like Cramer's method is one to go to, then we're going to be applying the Cramer's rule to solve this question, right? So once we apply the Cramer's rule, we're going to be able to get what our A naught is, what our A1 is, what our A2 is. Once we get this unknown coefficient, that is when they become known, then we'll now apply them back into the original quadratic expression that we had at the beginning of this curve fitting method. So once we apply that and we got to answer, then we can see that we've gotten a curve, or we've gotten an expression, a quadratic expression that is the expression that best fits into the curve. So that's the expression that best represents the curve, right? So let us now go further to solve the question that we're solving. So the same question that we solved using the Newton divided difference method, this question that we also solved, that we applied to solve the Lagrangian interpolation method, we're also going to apply it in this curve fitting method. So using the same set of data points. So solving, we're going to solve this question. All right, so now we want to solve this question now. The question states that we should obtain the best quadratic fit with the following data points given. So we have these data points given already. We have 0, 0, we have 1, 2, 3, 2, 6, minus 1. So I'm sure you are familiar with this question. We'll be solving it, we'll be using it for a very long time now. So we want to obtain the best quadratic fit using these same data points, right? So what matters the data points are given. Remember that, in fact, it's actually an assumption that governs, using these methods. It's an assumption that governs curve design. But we're going to talk about that in an entirely different tutorial. So now, we know that these data points are given, right? And another thing is that in curve design, you must make sure that the number of data points, which is one of the assumptions, you must make sure that the number of data points you are selecting is not that much. Why? Because this allows you to easily solve the expression, right? So try to pick as few number of data points as possible. That will still help you to get the expression for the either the polynomial or quadratic expression that best represents the curve, right? So going on with this question now, we said I want to obtain the best quadratic fit with the following data points. So these are data points, right? So now from this now we can get our x naught, y naught, x1, y1, x2, y2, x3 y3. I've said this already before. Our n in this question now represents the number of points. So now we have four number of points here, which means that our n minus 1 is equal to 3. So if n is equal to 4, then it simply implies that our n minus 1 is equal to 3. So which means that in this equation like this now, instead of me writing n minus 1, I can just replace each and every of those terms with 3. So we're going to have 3 here. We're going to have 3 here. We're going to have 3 here. But in actual fact, when you're solving this, you have to write this expression again, actually, and show that n minus 1 is 3. But because of it's already on the board, I can easily raise my hand. So that's why I'm doing like that. So n minus 1 is 3. N minus 1 is 3. 3. 3. 3. 3. 3. 3. So now what it's going to mean is this now. So we just try to get what this term is, because we actually need the actual values. We don't want this expression, we want the actual values. And then we can easily solve this. So for this first matrix now, so we already know this already. So I want to erase this now. I'm only going to keep data points. So we want to try to now get what each of those expressions, the value behind each of those expressions. So the points that we know are 0, 0, then we know 1, 2, we know 3, 2, we know 6, minus 1. So now to now get this matrix now, we want to get what summation of I equals to 0 is. So what this is now is that summation of I equals to 0, that is to 3 of 1, is going to be equals to, so we have 3 terms now. When I is 0, that is 1, plus when I is going to be equals to 1, we're still going to have 1, plus when I is equals to 2, we're going to have 1, when I is 3, we're also going to have 1. Adding them up, we're going to have 4. So which means that the value behind this term is 4. We know that now. So now for this also, the next here now, summation of I equals to 0 to 3 of xi. What this means is that x naught, because you are trying to substitute anyway you have I for the value of I, it is a summation. So in a summation you're trying to add up whatever you have as I is ranging from a particular point to another particular value. So now I is ranging from 0 to 3 now. So this means x naught plus x1 plus x2 plus x3. Right. So because of your time in exam, I now just have to write all this out. Because of explanation sake, something like this. So now for this now, what this means is x naught plus x1 plus x2 plus x3. So which means that by the time you add your 0 to 1, which is 1, plus 3, which is 4, then add that 4 to 6, you're going to have 10. So all this should give you 10. So you should have 10 by the time you simplify that. So for this next point now, if you try to do your summation of I equals to 0, that is 3 for your xi squared. What this means also is x naught squared plus x1 squared plus x2 squared plus x3 squared. So try to add it up now. X naught squared, 0 squared is 0, plus x1 squared is what? Still 1. X2 squared, that's 9. Then this 6 squared, that's going to be 36. So 36 plus 9, that's going to give us 45 plus 1, that's going to give us 46. So we're going to be having here 46. So that's going to be our value for that. So now for this next point now, we've already gotten the answer for this point, because this same term here is also the same term that is here. So we are going to have 10. We're also going to have 10 here again. So now this same point also, we've already gotten it here as x minus 2. So now this point here, since we've already gotten it already. So the next thing we need to find now is for this cubic term and also for this 1 raised to power 4. So to get our summation of I equals to 0 to 3 for xi raised to power 3. So that's going to be equals to x naught raised to power 3 plus xi raised to power 3, x1 raised to power 3 plus x2 raised to power 3 plus x3 raised to power 3. So by the time you solve this one, you are going to get 244. So what we just simply did here is that we did 0 cube plus 1 cube plus 3 cube plus 6 cube. You can arrive at this 244. So getting this value here, this term here, same thing as this term here, we already gotten this term now. So the term that is left for us now is to get this one. That is when raised to power 4. So to solve that now, We already gotten for this. Let me just make it some more compact. This is equals to 4. We already gotten for this. This is equals to 10. We already gotten for this equals to 46. Then this is also equal to 244. So applying the same method we have been applying so far. So if we do for our summation of I equals to 0 to 3 for xi raised to power 4, by the time you solve that one now, you're going to get 1,378. So 1378. That's going to be the value for that. So the next thing we also have to find out is that this term also can also be known. So to get those terms now, we're going to do summation of I equals to 0 to 3 for yi. So which means that we're going to be adding up our y values now. So 0 plus 2, that is 4, plus minus 1, that's going to give us 3. So we're going to have 3 here. So you also do the next value. We're going to have summation of I equals to 0 to 3 of xi yi. So what we're going to do here is that we're multiplying the product of x naught and x1 and y naught, then plus x1 times y1 plus x2 times y2 plus x3 times y3. That was just this means. So it means that if you do 0 times 0, that is 0, plus 2 times 1, that is 2, 2 times 3, that is 6, 6 plus the 2 you have here, that's 8. If you also come in and use 6 times minus 1, that's going to give us 6. So 8 and minus 6 is going to give us 2. So which means that our answer here is going to be 2. Then for the last term, which is summation of I equals to 0 to 3 of xi squared yi. So on evaluating that value, we're going to get minus 16. So what we'll just do is that we'll just slot these values that we now know of into this equation. So slotting them into this equation now, we're going to have this 4, then 10, then 46, then we're going to have 10, 46, then 244, then 46, 244, and 1378. Then also we're going to do something for the y side. So now we have been able to get the actual matrix expression for this. So we'll just go ahead and apply Cramer's rule. So if you apply Cramer's rule to this now, you'll be able to get what your A naught is, what your A1 is, and what your A2 is. Once you get those values already, put them inside the original equation, then you get your answer. So let's apply the Cramer's rule now. So what in Cramer's rule now, to get our A naught is going to be equal to our A naught is going to be equal to delta naught over delta. Our A1 is going to be equal to delta 1 over delta, and our A2 is going to be equal to delta 2 over delta. So what does delta represent in this question now? This delta represents the determinant of this matrix, right? So if you can get the original determinant of this matrix is just delta. So delta is just the determinant of this matrix itself. So to get our delta naught now, we're going to take this term and then put this term in this slot to get they'll find the determinant of this entire expression again. We're going to get our delta naught. To get our delta 1, we're going to take this term here, then substitute it for the term that we have here. So instead of having 10, you're going to have 3. Instead of having 46, we have 2. Instead of having minus 16, we're going to have, instead of having 244 rather, we're going to have minus 16. Then get the determinant of this particular matrix again. That gives us our delta 1. To get our delta 2, we're going to take this term, then substitute this term for this term, which means that instead of 46, we have 3. Instead of 244, we have 2. Instead of 137, we have minus 16. Then we also get the determinant for this matrix, particular matrix expression. Then we get our delta 2. Then we know we would have gotten our delta already by just getting the original determinant of this matrix. So by the time you evaluate this using this formula, it's A naught equals to delta naught over delta, A1 is equals to delta 1 over delta, A2 is equals to delta 2 over delta, and then you'd have gotten your A1, A naught, A1, and A2. So now let's just try to find what our determinant of the matrix is. And determinant now, our determinant is going to be equal to this. So here is going to be plus minus plus. So our determinant is going to be plus 4 or just 4. Then, because by the time you close here and close here, you're going to be having 46, then 244, then 244 again, then 1378. then minus 10, then the determinant of 10, 46, 244, then 1378, then plus 46, then plus 46, that will be 10, 46, 46, 244. So this is going to give us the determinant itself. So what we just did here is just very simple. We don't do anything much. We just did 4. Then by the time you close here up and close here up, I'm going to be left with the determinant of this. So now we have here 46, 24, 244, 244, 138. So then minus 10. By the time you close here and you close here, you left with this, and this. So that is 10, 244, 46, 1378. Then for the last 10, that is plus 46. You're going to be having, by the time you close here, you're going to be having 10, 46, 46, 244. So we try to solve this one out. You're going to be having, simplifying this further, you're going to have, it's going to be equals to 4, then into bracket. So normal determinant, I'm going to have 46 times 1378, then minus 244 times 244. So without this is going to give us the answer for this. Then minus 10 into bracket 10 times 3, 1378, then minus 46 times, then minus 46 times 244. Then the last 10 that is plus 46, the bracket 10 times 244, then minus 46 squared, 46 times 46. So this is going to give us our determinant. Alright, so by the time you compute this and you solve everything, so by the time you do this expansion and then you just try to solve everything you have here, you're going to arrive at the answer that your delta, which is your determinant of this matrix expression here, is going to be equal to, so our delta here is going to be equal to the value of 4, 7, 5, 2. So this is going to be our determinant for the matrix itself. So remember that we said now we are trying to get our A naught, A1, and A2. So to now get our A naught now, our A naught has to be the determinant of this delta naught over delta, right? So to now get this delta naught now, by the time you take this matrix here, put it in this first column. So instead of 4, you're going to have 3. Instead of 2, you're going to have, instead of 10, you're going to have 2. Instead of 46, you're going to have minus 16. So when you put this matrix, this entire column into this column here, then find the determinant of this matrix, you're going to get your delta naught. So to do that now, let's just replace what we have this value here. So we're going to be having 3, then 2, then minus 16. Then finding the determinant of this now. So let us do that. So let me just take note of the value that we have here now. So our delta now, we know that is equals to 4, 7, 5, 2. So let us now compute the expression for our delta naught. So to do that, we're also going to follow the same process we've been following since. So we're going to be having that our delta naught now is going to be equals to 3. That is going to be 46. Then we're going to have 244 here. We're going to have 244 again. Then 1378. Then that's going to be minus 10. Then when you close here and close here, you're going to be having 244. Then minus 16 and 1378. Then the last term is going to be plus 46. So when you close here and you close here, you're going to be having 2, then 46, then minus 16 and 244. So we just go ahead and compute this. Alright, so by the time you compute this, the answer you're going to get when you do this is that your delta naught is going to be equal to 1260. So now, since you already got your delta naught now, to now get your A naught is going to be equal to delta naught over delta, which is going to be equal to 1260 over 47 rather. So 4752. So when you do this, your A naught is going to be equal to, so using the calculator to solve that, you're going to get a 1260 over 4752. So that's going to be 35 over 1 32. So that's going to be value for your A0. So following the same method, you are going to get your A1 and your A2. So once you now get your A1 and your A2, remember that the original expression is this, that y, this is the original expression. The original expression is that y is equals to p of x. P of x is equals to A0 plus A1x plus A2x squared. So once you get your A0 to A1 and A2, just slot them back into there. So you put your A0 here, put your A1 here, and put your A2 here. So we can see that this is the equation, that is y equals to p of x, the quadratic equation that best fits the curve, and then that's going to be your answer. So that's all.